Hello friends, this is Anmesh and welcome to the Get Mantra. So in this video we are going to start with a new topic, that is transconductance, right? Is transconductance, right? So before starting this topic, let's see the waveform between the ID drain current and the gate to source voltage, right? So here is the drain current, here is the drain current, and here is the gate to source voltage. As we know that when the gate to source voltage is less than the VTH, then the inversion layer is not formed in between the source and the drain, and hence there will no current flow when the VGS is less than the VTS. Let's suppose this is the VT naught, right? And when the VGS is greater than the VT naught, then the channel is formed between the source and the drain, and hence when we apply a VDS, then the current will flow into the channel. Okay, so we are drawing this ID VGS curve at a constant VDS, right? At constant VDS we have applied the VDS here. Okay, at constant VDS, right? Because because without applying this VDS, the current will not flow into the channel. So here we have applied a constant VDS, that is a drain to source voltage, and now we are increasing the VGS. So when we are increasing the VGS from 0 till VT naught, okay, from 0 till VT naught, our current will be 0, our drain current will be 0 here, our drain current will be 0, right? Our drain current will be 0, and when the VGS is greater than the VT naught, our drain current, okay, will start increasing, right? Start increasing. Okay, so let us see this curve between the ID and the VGS. So here, okay, in the starting we are seeing the curve is, okay, curve is not linear. Okay, the curve is non-linear, curve is not linear, and here we are seeing the curve is linear. Okay, so here our MOSFET is operating in the saturation region. Hence our drain current is increasing non-linearly, and here our MOSFET is operating in the linear region. Okay, the linear region. Hence our drain current is increasing linearly. Okay, increasing linearly, and we are drawing this at a constant VDS, right? So this is this is called as the ID-VGS curve, or the transfer characteristics curve, because here the input is VG, okay, that we are applying at the gate voltage, and the output is ID. So this is the curve between the input and the output. Hence it is also known as the transfer characteristics curve. Okay, it is also known as the transfer characteristics curve. Okay, or we can say with the ID-VGS curve. Okay, yes, curve, right? So what we have seen here, when the our applied gate voltage is less than the VT naught, the drain current is 0, and when the this gate voltage, applied gate voltage, is greater than the VT naught, Okay, and this VT naught is the threshold voltage. This VT naught is what? This is the threshold voltage. Then the drain current is flow. The drain current is flow. And initially, our MOSFET will be in saturation region, and hence the drain current will be here increasing non-linearly. And here the drain current is linearly increasing because our MOSFET is in linear region, right? So what we can get from this IDVGS curve? So this from this IDVGS curve or from this transfer characteristics curve, we will get a important parameter. Okay, important parameter. This is that parameter is known as the transconductance. Is known as the transconductance. So what is the transconductance? The transconductance is nothing but the change in the output voltage. Okay, the change, sorry, not voltage, the change in the output current when we are changing only the input voltage. Okay, then what is the transconductance? I am writing here. Okay, this trans here, right? So what is the transconductance? Is change in, okay, is change in output, is change in the output. What is the output here? The drain current. Okay, the drain current due to the change in only input or input only, due to the change in input only. What is the input here? VGS. So the transconductance is an important parameter, and it's defined as the change in the output, and the output here is drain current due to the change in the input only. We are changing only the input and seeing how the output respond to change in the input. Okay, we are seeing here, we are observing here how the output, okay, respond to the change in the output, to change in the input. Okay, so in saturation region, okay, in saturation region, okay, let's assume, okay, let's assume channel length parameter, that is the lambda, will be equal to 0. This means no channel length modulation happen, no channel length modulation happen, right? So here the drain current is 1 by 2 Newman. This is for the N MOSFET. Okay, COX W by L, right? VGS minus VT naught, right? Now we are going to derivate this, differentiate. We are going to differentiate this drain current. We are going to differentiate this drain current with respect to the VGS. Okay, will be equal to 1 by 2. Okay, Newman COX W by L. Okay, here 2. Okay, VGS minus VT. Okay, then this 2 will be cancelled out, and this GM, okay, this is the transconductor, is nothing but the DID upon dVGS. Okay, differentiation of the drain current with respect to the gate to source voltage, and it will be equal to the nu n, okay, COX W by L, okay, and VGS minus VT naught, where VT naught is the threshold voltage. Right? So here this is the transconductor. So this is the transconductor, right? So transconductance will be equal to the DID upon VGS. It will be equal to the Newman COX W by L VGS minus VT naught. Okay, and this is in the saturation region. This is transconductance in saturation region. Now we are going to draw the graph between the GM, okay, transconductance and the VGS here, right? The transconductance here, the VGS, right? So the graph between transconductance and VGS will be like this, right? Because it is starting from any VT now, okay? So this is nothing but the we can say this is nothing but the voltage bias, okay? Let me change the voltage bias. This curve is called as voltage bias curve, okay? And this is the curve between the GM and the VGS, right? Now we can know that, okay, we can know that ID will be equal to the insaturation. Let us assume this is the equation 1 and this will be the equation 2, right? Now we can say that, okay, from here, from equation 2, from equation 1, that will be equal to the ID will be equal to 1 by 2 nu n cox w by L. This is the equation 1, okay, VGS minus VT naught whole square. Now what we are going to do here, we are going to calculate VGS minus VT naught, right? And this will be equal to the 2ID, and this will be equal to the 2ID, okay. So here this VGS minus VT naught will be equal to the 2ID divided by, okay, nu n cox w by L, okay. Now let us assume this is the equation 3. Now we are putting equation 3, okay, in equation 2. So what will be our equation 2? This will be the our equation 2, hence GM will be equal to, okay, nu n cox w by L and VGS minus VT naught. Now we are putting this VGS minus VT naught will be equal to this, so this will be equal to the nu n cox, right, w by L, okay. This will be root over, right, and root over 2ID divided by nu n cox w by L. So this will be equal to, GM will be equal to root of 2 nu n cox w by L into I, okay. So this is the new formula for the transconductance, okay, in the saturation region, right? So this will be the new formula for transconductance in the saturation region. Please remember this formula because this is really very important, okay. This is really very important, right? So what will be the transconductance in the saturation region? This is the another formula that will be equal to the root over, okay, root of 2 nu n cox w by L into ID. Now I am going to draw, okay, the curve between this GM and the ID, okay. I am going to draw the curve between the GM and the ID here, okay. What is this? This is the GM, right, This is the transconductance and this is nothing but our drain current. Okay, now this curve will be like this. Okay, so this curve will be like this. It will be parabola. It will be a parabola. Okay, so the curve will be like this. Okay, this. So this is the curve between the transconductance and the drain current, and this curve is called, okay, the current bias. Right. Now let us see the third formula for the transconductance. Right. So here we are having from equation 2, okay, from equation 2, okay, Gm will be equal to nu and cox w by L, okay, vgs minus vt naught, and we know that id will be equal to nu n is 1 by 2 nu n cox w by L, okay, vgs minus vt naught. Now we can write this as 1 by 2 nu n cox, okay, zw by L for the nmos, okay, vgs minus vt naught into vgs minus vt naught. Right. Now see here, is nothing but the our transconductance, right? So we can write here id will be equal to, okay, id will be equal to gm, because this is the nothing but the transconductance, gm into, okay, gm into vgs minus vt naught. So here we can write gm will be equal to the id divided by vgs minus vt, right? And this will be the our third formula, okay, for the transconductance in the saturation, right? This will be the our third formula for the trans. Okay, so now we are going to draw the curve between this id, sorry, this is gm and gm, and this is vgs, and this curve like hyperbola because it is inversely proportional to vgs, right? So this curve will be like this. So this curve will like this, right? So this is known as the technology, this is known as the technology bias, right? So we have seen here the three different formula for the transconductance, and we have also seen what is the transconductance, right? So, and we have seen what is the transfer characteristics curve here. So transconductance is the change in the output due to the change in the input only, right? So here the output will be id and the input will be vgs, right? And we know that in saturation region our drain current is, okay, in saturation region our drain current is this one, id is equal to the 1 by 2 nu n cox w by L vgs minus vt naught. Now we are going to differentiate this drain current with respect to the vgs, and we are getting the transconductance gm will be equal to the nu n cox w by L vgs minus vt naught. And we have drawn the curve between the gm and the vgs, and this curve is known as the voltage bias. Now we are taking this first equation and this second equation, and from here we have derived another formula for the transconductance, and this will be equal to the Gm will be equal to the root of 2 Newman COXW by L into ID, and this is the waveform or the graph between the Gm and the ID. This is called as the current bias. Okay, now this is the third formula for the transconductance, and this will be the equal to the Gm equal to the ID, okay, divided by Vgs minus Vt naught. Okay, this is also the important formula, and this graph between the Gm and the Vgs is hyperbola, and this is nothing but this graph is nothing but the technology bias, right? We say this curve is a technology bias curve. Okay, so this was the discussion about the, okay, transfer characteristics curve as well as the transconductance for the MOSFET. Okay, and here we can say this is the AC resistance or incremental resistance or the output resistance. Okay, or the output resistance, and we are taking when this and we are taking this G naught will be equal to the 1 upon R naught. Okay, will be equal to the lambda in this G naught is nothing but the conductance. Okay, so please do not confuse between the transconductance of the MOSFET and the conductance of the MOSFET, right? The conductance of the MOSFET will be equal to the G naught and will be equal to the lambda and the ID, lambda into ID. And the transconductance having the three formula. This Newman CFW by L, another one is root of 2 Newman CFW by L into ID, and the third one is ID upon VGS minus, right? Now we are going to see the contact, okay, the contact between the semiconductor and the metal, right? So here let us consider, okay, let us consider this one is metal, this one is the, right, and this one is semiconductor. One is, let us say, n-type semi, okay, right. So when we are talking about, okay, when we are talking, okay, here we are talking about the contact between the metal and the n-type semiconductor, right? So here, okay, here the current will be flow when we are talking about the junction between, okay, when we are talking about the junction between the metal and the semiconductor, okay, then the current and the electron will be flow, okay, the electron will be flow through the junction. Okay, this flow of the electron is depending upon the work function of the metal as well as the semiconductor. So here, if we are talking about the transfer of the electron, here if we are talking about the transfer of the electron through the junction, and this is the junction is in between the metal and the n-type semiconductor. So the transfer of the electron through the junction, okay, through this junction is totally depend upon the work function of the metal as well as the n-type semiconductor. So, so our second one is, what is the work function? Okay, what is the work function? So let us define the work function for the metal. This will be equal to the phi n, and the work function for the metal is defined as minimum amount of the energy, the minimum amount of the energy that required to escape the electron, to required to escape the electron, okay, from the metal, okay, at absolute zero temperature is known as the work function. Here I repeat again, the work function of the metal, that is the phi m, is defined as the amount of the energy, okay, is required to escape, okay, the electron from the metal at 0 degree temperature, or we can say at the absolute zero temperature, right? So we have seen the work function. Now we have the two cases, right? We have the two cases. The work function, in the first cases we have assumed the work function of the metal is greater than the semiconductor, and in the second cases we have assumed the work function of the metal will be equal to the work is less than the work function of the semiconductor, right? And in third case, there is total three cases, and in third case we have assumed the work function, okay, of the metal is equal to the work function of the semiconductor, right? So here we knew about the three things, okay. The first one is, if there is a junction exists between the metal and the n-type semiconductor, or a metal between the metal or any type of semiconductor, either it will be the n-type or p-type, then the movement of the electron, or the transfer of the electron, or we can say the flow of the electron from metal to n-type semiconductor, or from n-type semiconductor to metal. This means the flow of the electron through the junction is totally depend upon the work function of the metal and the work function of the semiconductor, right? So if we have assumed, if the work function of the metal is greater than the work function of the semiconductor, this means the semiconductor can easily, this means the semiconductor can easily, okay, escape the electron, okay, from its Fermi energy level, or from its, okay, conduction band, we can, to the vacuum, okay. And whereas the metal required a large number of to escape the electron, okay, to escape the electron at 0 degree temperature or at the absolute temperature, right? So here, in simple word, we can say the energy required to escape the electron from the center lesser than the energy required to escape the electron from the metal. So if there is a junction exists between the metal and the semiconductor, okay, and if we join this metal and the semiconductor, then what happens? See, as we know that there is an infinite number of the electron exist in the metal, right? Exist in the metal, and in n-type semiconductor the electron will be of the majority charge carrier and the hole will be of the minority charge carrier. Now since the phi s is phi m is greater than phi s, this means the work function of the metal is greater than the work function of the semiconductor. So when we keep in contact, okay, the metal as well as the n-type semiconductor, when the metal and the n-type semiconductor is keep in the contact with each other, then the electron, okay, electron will easily flow from the n-type semiconductor to the metal, because the work function of the n-type semiconductor is less than the work function of metal. So when the electron, okay, so how we are denoting this type semiconductor like this, okay, and here this is, here exists the large number of the, right? So electron will be easily move from n-type semiconductor to the metal, because the phi s is less than phi m, right? Because the phi s is less than phi m. So here, so here electron will be moved, okay, and only immobile depletion region will exist, okay, and only immobile depletion region will exist, okay, and here negative charge will be exist. So here, before before coming the contact the metal and the n-type semiconductor, our energy band diagram is like this, okay. Here we can easily see the amount of the energy required to move the electron or to escape the electron is, okay, phi m, that is the work function, and is greater than this phi s, okay. Now let us see here one more, okay. So here we have to, okay, escape the electron from metal to the vacuum. So here, since the phi m is greater than the phi s, so here to escape the electron from metal it's required the more and the more energy. So the alternate way we will do, we will escape this electron from this Fermi energy of the metal to the EFN, and okay, and from EFN it will goes to the vacuum by the E phi s, okay, since E phi s is less than the E phi m, right? So this energy, the difference between this energy level is known as the E, and the phi v, nothing but the E and the phi v, and this phi v is nothing but the phi m minus eta, right? This phi v is nothing but the phi m, this minus eta, right? So when we are increasing this work function of the metal, this phi b will be increased, right? This phi b will be increased if we are increasing the work function of the metal, right? Okay, so we have seen here, okay, when we keep the metal in a contact with the n-type semiconductor, what happened, okay, what happened, the depletion region will be formed toward the n-type semiconductor, and hence here will be the positive voltage, okay, and here will be the negative voltage, okay, and a bolting electric field will be exist from here to here, this will be able, okay. Now we see the energy band diagram when the metal and the n-type semiconductor keep in the contact, okay. So this is after contact, okay, and we are not applying any biasing here, so when the Fermi energy level of this metal will be equal to the Fermi energy level of this semiconductor, the movement of the electron will, okay, stop from n-type semiconductor to the metal or from metal to the n-type semiconductor, okay. So here the Fermi energy level of the metal will be equal to the Fermi energy of the n-type semiconductor, and a uphill will be exist, okay, in the energy band diagram, and hence the electron cannot move, okay, from the semiconductor to the metal, because for moving the electron from semiconductor to the metal we have to apply a large amount of the voltage, right? And this q into v naught, and this q into v naught will be equal to the phi ms. Okay, and this phi ms, okay, this is the metal and semiconductor work function, nothing but the phi m minus phi s, right? So, and this will be nothing but the a into phi b. Okay, this will be a into phi b, and this is the a into phi b. Now, let us see what happened when we are applying the forward bias. Okay, so let us see. This is the metal. Right, so when the metal is come in the contact with the type semiconductor, the depletion region will be formed here, right? And now for the forward bias, we have to apply the negative voltage here and positive voltage here. Okay, and due to this, right, the electron, due to this, the energy band diagram, the energy band diagram of the metal will be come down, will come down, and the energy band diagram of the n-type MOSFET will be go up, right, will go up. Why? Because here the bolting electric field exists between the, here the bolting electric field will exist, a bolting, okay, a built-in. And when we are applying the forward bias, the electric field is this one, a, due to the external applied the voltage, due to the externally applied voltage, the electric field will like this, and these two electric field are in opposite to the each other. So this electric field that is obtained by applying the external voltage will cancel out this bolting electric field, and due to that, okay, due to that, the gap, okay, this is the phi b, this is the a into, okay, and due to that, the gap here, this gap will be reduced, and now this gap will be equal to the q into, or we can say e into v naught minus va. Okay, e into v naught minus va, or q into v naught minus va, we can say. Okay, so here va is the applied forward bias, applied forward voltage. So when we are applying the forward, okay, voltage, okay, this external electric field will be, okay, cancel this bolting electric field, and due to this, okay, the in the energy band diagram is, okay, will be like this. Okay, here because the positive voltage is applied at the metal terminal and the negative voltage is applied at the n-type semiconductor, the energy band diagram will be attracted, okay, will be attracted, or we can say will push down, okay, toward the metal, okay, and the energy band diagram will push up toward the n-type semiconductor. And now this, the height of the uphill will be decreased, and hence the electron is easily moved from semiconductor to the metal. Okay, here the difficulty, okay, here there was a difficulty in the movement of the electron from semiconductor to the metal due to the due to uphill. So due to the uphill, the electrons were not able to move from semiconductor to the metal, but after applying the forward bias, this height is decreased, this height is increasing, and hence the electron can easily move, okay, from semiconductor, from n-type semiconductor to the metal, right? Now what happened when we are applying the negative bias, right, reverse bias? So here is again metal. So this is metal, nothing but the n-type semiconductor. Okay, we have seen here that the difference is Bolton electric field will be exist here, will be equal to the V naught, the Bolton voltage, right? Okay. Now for the reverse bias, we have to apply, okay, the negative voltage here and the positive voltage here, and because of the applied voltage, the electric field will be like this, and this electric field is supporting the built-in electric field. Okay, this electric field is supporting the built-in electric field, and due to this applied reverse bias voltage, that will be equal to the VR. Okay, the height of the uphill, the height, okay, this height will be increasing, this height is increasing, right? This height will be increasing, and because of that the electron cannot move, okay, the electron cannot move from n-type semiconductor to the metal, right? And why the electron cannot move? Due to the uphill. Okay, so when we are applying the negative voltage at the metal and the positive voltage at the n-type semiconductor, this energy band diagram at the metal will be pushed up, and the energy band diagram at the n-type semiconductor will be pushed down, and because of that, okay, will be pushed down, okay, this will be pushed down, okay, this will be pushed down like this, and this will be go up, and due to this the uphill, okay, the height of the uphill will increase, and hence electron cannot be flow from semiconductor to the metal, right? Remove this, it will, right? So we have seen here the contact between the metal and the semiconductor, and we have seen that in, okay, when we keep, okay, in contact, when we keep the metal contact with the n-type semiconductor, and if we assume the phi m is greater than the phi s, then in the forward bias, the electron can easily move from n-type to the electron, and in the reverse bias, electron cannot move from semiconductor to the metal. And when these two come in the contact, the electron can, because of phi. So we can say, okay, here we can say when we are applying the voltage like this, okay, so for positive bias, so okay, for the positive or for the forward bias, okay, for the forward bias the output will become like the input, okay, For the forward bias, the output will become like input, and for the reverse bias, the movement of the electron will not happen. Hence, this will come like this. A very small voltage will be present here. Now, again for the forward bias will become like this for the right. So we can say this operation is nothing but this operation is look like a rectifier. Okay, rectifier, right? So we can say that when the contact between the metal and the n-type semiconductor, and when the phi m is greater than phi s, then the rectifying contact is formed between the metal and the n, right? Okay, now let us see what happened when the work function of the semiconductor is greater than the metal. So when the work function of semiconductor is greater than the metal, see here, the work function of semiconductor, okay, is greater than, this is the work function of the semiconductor, right? This is the work function of the semiconductor. This is greater than this work function. So when this metal and the semiconductor come in the contact with each other, each other, the metal will be, okay, release, or the metal will escape. In metal it will be easy to escape the electron as compared to the semiconductor. So when this metal and the semiconductor is come close to each other, or come in the contact with each other, this metal will easily, okay, easily, okay, release the electron. Okay, so here we can say, okay, let me make here between the metal and metal with the the n-type semiconductor. Now the metal can easily release or easily escape the electron. Hence, the positive depletion is from here. Depletion, since the metal have the large number of the electron, hence this positive region will be eliminated. Now the depletion region will be exist here. Okay, right. Now when we are applying the forward bias, right? When we are applying the forward bias, what happens? So now when we are applying the forward bias, this is the metal, the semiconductor. For forward bias we have to apply plus here, the negative sign here, right? So what happened when we are applying the positive voltage here and the negative voltage, okay, negative terminal the voltage here, the energy band diagram, as the energy band diagram at the metal of the metal will be pushed down, okay, will be pushed down, okay, this energy band diagram will be come down, and the energy band diagram of the semiconductor will be go up, okay, because the negative terminal of the voltage applied. So the energy band diagram, finally the energy band diagram, okay, of the metal and the semiconductor contact will be come like this, and here the electron will be easily flow from semiconductor to the metal. Now when we are applying the reverse bias, okay, when we are applying the reverse bias here, when we are applying the reverse bias, right, this is the metal and this is the semiconductor. So here we are applying the negative voltage, and here we are applying the positive voltage. So here here okay, when we are applying the reverse bias, okay, so here we are applying the, for the reverse bias, negative voltage, and here we are applying the positive voltage, then this energy band diagram will become, this energy band diagram will become down, and this energy band diagram will be go up, right, and the resulting energy band diagram will be like this. Okay, when it come down, okay, when it come down, and when it go up and when it come down, the resulting energy band diagram will be like this. Okay, like this. Okay, and here the electron can easily go from metal to the semiconductor. Okay, metal to the semiconductor, right. Okay, so here we can say that, okay, here we can say that when the phi m is greater than the phi s, when the phi m is less than the phi s, okay, the depletion region that form in the semiconductor side is not effective, but when the phi m is greater than the phi s, but when the phi m is greater than the phi s, the depletion region form, okay, in the inside is really very effective, and it's make the contact as a rectifying contact. Okay, now I am writing here conclusion. Okay, I am writing here conclusion that, okay, the work function of the when the work function of the metal, okay, when the work function of the metal is greater than the work function of the semiconductor, okay, n-type semiconductor, the depletion region form to the semiconductor side, okay, form to the semiconductor side, and it is it is very effective, and make contact as rectifying contact, right. And when phi s is greater than phi m, right, when the phi s is greater than phi m, okay, the depletion region will be formed in the metal side here. Okay, here the depletion region will form in metal side. This depletion region is not effective, and hence is make the contact as a ohmic contact. Make the contact as a ohmic contact. Okay, so in the ohmic contact, when we are applying the voltage here, we are getting the voltage like this. But in the rectifying contact, when we are applying voltage like this, okay, when we are applying the voltage like this, okay, we will get the voltage like only for the positive bias, or only for the positive half cycle, or only for the forward bias, and we are not getting any output voltage for the negative bias or in the reverse bias, right. And now again we are getting the voltage, output voltage for the forward bias, right. So this will be the forward bias with the for the reverse bias. Now, okay, now for the gate or for the ES, we have for the gate or for the ESC, we have to remember only two things, that this is the n-type semiconductor, this is the p-type semiconductor, okay, and this is the metal, right. Now see here, for the n-type semiconductor and this is the metal. This is nothing but the metal. So for the n-type semiconductor, when okay, for the n-type semiconductor and the metal connection, okay, when the phi s, okay, the phi s is greater than phi m, the contact between the metal and the semiconductor, that will be the n-type semiconductor, will be the ohmic contact, the ohmic contact, okay. And we generally prefer the ohmic contact in the circuit, okay, in the circuit, right. And the second, when phi m is greater than phi s, then the contact is not the rectifying, and the contact is not the rectifying contact, or we can say Schottky contact. Similarly, for the p-type semiconductor and the metal, when the phi m is greater than the phi s, the contact will be called as the ohmic contact. Okay, the contact will be called as the ohmic contact. When s will be greater than phi m, contact will be rectified. Okay, so we have seen here. So in this video we have seen what is the transfer characteristic or what is the transconductance. We have seen the three formula for the transconductance, and after that we have seen the contact between the semiconductor and the metal, and we have seen for the n-type semiconductor and the metal, if the phi s is greater than the phi m, then the contact will be the ohmic contact, and if the phi m is greater than the phi s, then the contact will be the rectifying contact. Okay, and for the p-type semiconductor and the metal, okay, the p-type semiconductor and the metal, if the phi m is greater than the phi s, then the contact will be the ohmic contact, and if the phi s will be greater than the phi m, the contact will be the rectifying contact. Now in the next class we are going to see the flat band, okay, the flat band, okay. So when the flat band will exist, the flat band will exist when the phi m will be equal to the phi s, when the work function of the metal will be equal to the work function of the semiconductor, then the flat band exists, okay. And in the next, okay, video we are going to see, okay, the energy band diagram for the different region of the operation like accumulation, inversion, depletion. So thank you for listening, okay, thank you so much.